Hi everyone, my name is Rhauani Fazul. I'm a graduate student in computer science at the Federal University of Santa Maria, and today I present a work developed under orientation of Professor Patricia Pitthan that is called the Node Status as a Prioritization Strategy for Replica Balancing in a HDFS cluster. Here we have an overview of how this presentation is going to work with the theoretical fundamentation and the proposed solution. So, to deal with high volumes of data in distributed environments, dedicated tools such as Apache Hadoop are widely used. One of the main components of Hadoop is its distributed file system, the HDFS. To ensure reliability and availability, even when running on clusters of community hardware, HDFS leans on data replication. So, when a file is inserted in the HDFS, it is split into data blocks. Each block is then replicated and distributed between the data nodes. To determine which nodes will receive the replicas of each block, the name node follows a replica placement policy, or simply RPP, that optimizes the replica distribution by using hack awareness. However, the RPP does not ensure a full balanced replica distribution, thus contributing to cluster imbalancing. Replica imbalancing also occurs in situations like the addition of new data nodes into the cluster, as it results in a large discrepancy between the data held on the nodes. This impacts the data locality and can prevent the HDFS to explore the computational resources in an optimized way, degrading its overall performance. One way to redistribute the data spread across the cluster is by using the HDFS balancer, a Hadoop daemon focused on replica balancing. The balancing is driven by a threshold that limits the maximum difference between the utilization of each stored device and the average utilization of the cluster. Although it was designed to run in the background, the balancer operates in a generalized way, and it does not consider parameters such as the communication traffic of the nodes and the volume of data to be transferred. So, to optimize the replica balancing process, we created a customized policy for the HDFS balancer. This policy is based on a priority system, where the priorities are grouped into 4 categories according to their behavior. This work focuses on the priorities of the node status category. First, we have the node utilization priority, which reorders the list of the stored device groups based on the data volume stored in each group. This increases the chances that the group with the highest utilization in the cluster will be primarily paired with the group with the lowest utilization, and so on. With that, we can optimize the matching of the source and target nodes. The second priority is the node classification one, which aims at a minimum balance in the cluster. Basically, it creates an effort to reduce the number of data transfers required to balance the data distribution in the cluster, and with that, it is possible to reduce the execution time and the throughput consumption required for balancing the data. Last but not least, we have the node load priority, that considers the number of active connections the nodes in order to determine the volume of data to be moved between them. To do this, we collected and registered for each data node the receiver count. This attribute gives an estimated number of active connections in the target node. Based on the receiver count, the node load is established from the min-max normalization that helps us to keep the estimated load of the nodes in a controlled interval, and then it can be used to weight the amount of data to be sent or received so that less overloaded nodes are prioritized for data transfers. To validate and evaluate the effectiveness of the implementation, we conducted an experimental investigation on Grid 5000 platform using Hadoop with 10 data nodes. The data load was performed by test.fsio and with the benchmark we write 10 files of 25 GB each. The average utilization of the cluster after the data load was about 23%. The table here shows the occupation in gigabytes and the utilization percentage of each data node in 2 scenarios. Before the replica balancing, that is with the data distribution based on the default RPP, and after running the balancer with the proposed solution and a threshold of 5%. With the balancing, as we expect, the data volume maintained by each node is less divergent. This can be seen here by the reduction in the standard deviation. The second column here exhibits the load estimate of each node based on the min-max normalization. Highlighted are the data nodes that were considered busy by having a high flow of communication in their nodes. The data node 6, for example, was busy, and so its utilization was reduced to the upper balancing limit, that is the cluster average plus the threshold. It is important to notice that the data node 9, given it was already between the threshold, did not send or receive data. It reinforces the effort of the no-load priority to minimize the additional overhead caused by the balancing process on busy nodes. To investigate possible performance improvements, we run the test FSIO in reading mode 15 times. Based on the percentage change here, we see a reduction in the time needed to read the data stored in the HDFS after replica balancing, and an increase in the application throughput and I/O rate as well. In this experiment, the execution of the balancer with our solution took about 43 minutes to complete and moved 73.5 gigabytes of data. If the balancer was running with its default policy, the data volume to be moved would be about 221 gigabytes, which will demand 135 minutes to be relocated. So in this work, we proposed a customization for the native balancer of HDFS based on balancing priorities. This strategy prevents nodes that are already experiencing overhead periods from being further impacted by the balancing operation. Also, we incorporate the concept of minimum balancing into the HDFS, moving as little data as possible to make the utilization of each node to be between the balancing threshold. The evaluating results showed that our customization allows us to optimize and make the HDFS balancer operation more flexible by reducing the time and bandwidth consumption required to achieve the system balancing. Future work involves analyzing the behavior of the priorities with Hadoop instance on heterogeneous environments and with node failure scenarios, and running different stress testing benchmarks for HDFS. Here we have the bibliographic references used in this presentation, and that is it. Thank you all for your attention.